Okay, so welcome everybody to the lecture series Environment, Climate, Sustainability from Knowledge to Action. And as announced last week, we will have this session totally in English, so also the questions later, please. So if you have read the description of this course very carefully, you have seen that it is really about the connection between science and public administration. So it's not so much about what we can individually do in terms of climate, sustainability, and the environment. It's also not so much about politics, even though obviously politics play a very important role when we talk about public administration. But it's really about this interface between science and public administration and people working there, and how can they interact with each other? How can they interact maybe even better with each other? And as always, we will have these two talks now. We'll have questions and a discussion at the end. So if you have any questions throughout the talks, just note them down, and we will try to answer as many questions as possible at the end. And also, don't forget, it's about questions. So you're absolutely allowed to make statements, that's fine, but it would also be nice to always have a question included in that. And now, I'm already very happy to introduce our first speaker of this session, Maria Zunabovic-Pichler. She did her doctoral studies in food science at the University of Natural Resources and Life Sciences, so the BOKU, here in Vienna. And she actually worked for quite a long time. We just were talking before, for 17 years at BOKU in different fields, the food sciences, but also sanitary engineering and water pollution control. She's a lecturer at the University of Vienna, at BOKU, also in Graz. And since 2021, she is the head of the water quality unit at the Municipal Department 31, which is known as Wiener Wasser in German, Vienna Water. And I'm very much looking forward to your talk, and a warm welcome to Maria Zunabovic-Pichler. Thank you.
Thank you very much, Timo, for the kind introduction to my person and my working history. So as you heard, everything has to do with food, and water is also a food. I think in recent time, from a regulative aspect, water was not included as a food from a regulation aspect, and this is tragic, as we know already that drinking water is the most important food and food component in a lot of foods. So, and I'm happy to share with you some experiences about my work and about our challenges that we face at Wiener Wasser and also in the city of Vienna regarding future aspects, water demand and everything. First of all, I would like to give you an input on my content. So I think most of you already had contact with Vienna drinking water. Hopefully you consume it quite a lot. This is very important, as it is the cheapest, healthiest and climate friendliest food you can obtain in Vienna. And also about our work and our working capacity. Probably some of you are not aware that we are constituted of about 600 persons that are responsible for the distribution of water and implementing technical aspects and new state of art in the field of water and reconstruction of historical buildings. And finally, I would, next to the tackling about climate change, I would like to talk about the strategy for the future of Vienna Water. This is a very important paper, a publication we have written in the recent years and started in 2020 with working out what is the future and water demand of Vienna Water, or of the population in Vienna. And so we wrote a strategy where to invest and where to enlarge our capacities in a growing city like Vienna is. So as my follow-up speech is talking about a measurement of water quality and the technical aspects, also I will give a kind of input on water quality aspects relevant to the resources that we have in our alpine system. So the scheme is published also in at our homepage of Vienna Water. I don't know if you know where the Vienna Water comes from. It has a clear alpine source. The Vienna drinking water originates from the lower Austrian part and the Styrian Alps, and where the area is highly protected, of course, we have to conserve the zones and protect them from conflicts of interest like tourism, agriculture, and etc. So we call it in the regulative aspect the Schutzgebiete. And the water is primarily sourced from the Rax, Schneeberg, Schneealpe. So somebody who is going for hiking knows this region very well. And for the second spring water main, we have the Hochschwab-Massiv. This is the northern Hochschwab in Styria, which is a big, as you see also in the protection zones on the left-hand side, where the Kleffer Spring, the most discharging source is. Here is the largest protective zones. From the size of the protective zones, we are talking about 600 square kilometers of Wasserschutzgebiet, what we're talking about, and it's owned about 350 square kilometers are owned by the city of Vienna. So, of course, we are highly interested to own these areas to protect of future interests and also other problems that maybe arise from environmental pollution. So you see that 90% of the water catchment is followed up by karstic spring waters, and 10% amount is from groundwater. I will go into this later on. So this is very important also to have a supportive system for the karstic spring sources. The demand, this is high. This is very high and it is increasing. The mean demand is about 390,000 cubic meters per day. So it's increasing already. We are in the median about of 400,000 per day. So this balance is very important when you consider 70 sources, so 70 springs that are in these regions distributed in the first and the second spring main water. You have always to balance out the springs, the karstic springs, with the demand to Vienna. The travel time of the water is about up to 36 hours, which is gravitatively transferred to Vienna. This means the water is transported to Vienna without any pumping, and this gravity aspect is, of course, is used also for the electricity and power energy that we apply also with 16 devices. So on the way to Vienna. I think this is very important. And due to the protection areas, the water is marginally treated, that is coming to the southeast to Vienna. This means that we make a safety disinfection. This is the treatment for the karst spring waters, which are highly vulnerable to different aspects of environmental events. So just a kind of recommendation. I don't know if you have already seen, there was a Servus TV documentation on the Vienna water. And it's very nice and impressive and full of pictures to explain the work of Vienna water people here. Yeah, this is already the resources that I've mentioned before. So you see the conservation area is very large, by the half. When you compare it to the size of Vienna, it's almost the size of Vienna. And what does it mean? In the practical aspect, you have to manage these protective zones. This is just possible with people and collaborations with other Magistratsabteilungen, so divisions in Vienna, so which is, for instance, the Forestry Department, the MA 49. Also, we have high collaborations with MA 45, Wiener Gewässer, where we have also in our groundwater works a lot of collective interests to protect areas. So this is, I think, a very important aspect. And see also we have, from an historical aspect, almost 82 kilometers of tunnels, which are directly passing through mountains. So this is naked mountains that is up to 1,000 meters above. You have a kind of mountain through this tunnel where our people in maintenance situations also enter this regularly. This is quite often, so at almost up to 4 times a year where this is inspected. So as it is an historical building, of course. Yeah, the groundwater areas is also very important. These groundwater areas are in the region of Vienna, so on the border of Vienna. You know probably the Lobau-Wasserwerk, and you know the Danube Island, and you know Nussdorf and Moosbrunn in the south of Vienna. Mainly these types of water are riverbank filtrates. So the filtration process that happens in the mountains is quite comparable to those in poor groundwaters. Probably the vulnerability is of these groundwaters lower than in karstic spring waters, as you have a lot of karstification and caves where a lot of hole systems develop in mountains. They save the water. And of course, in rainfall events, I will show you a kind of picture how this is managed. So these are very important backups to the first and second spring water main, as we deactivate it regularly. And the water that is coming to Vienna, just an impression to you from the southeast, this is passing in Mauer in the 13th district and in Rosenhügel. And on the left-hand side, you see a lot of water reservoirs. As Vienna is a kind of mountainous city, we use the gravity forward also in the distribution field. So we do not pump the water within Vienna, so we save a lot of energy. So the water is balanced in these reservoirs in Vienna, and of course, if there are highly needed sudden water demands or some kind of firefighter actions, then of course, and swimming pool fillers are ongoing, then these reservoirs are balancing out the demands. And from the left to the side, from the west to the east, the water is transferred in pressure zones, and the highest pressure zones, of course, with ongoing lower pressure, is going over to the 23rd and 21st district, which is the lowest point in Vienna. And of course, karst spring waters also reach over the Danube. So please be sure that there are bridges and pipes passing these bridges, that the water is transferred. This is very important. So I think you see it's highly complex with 3,000 kilometers of pipe system. So this is a lot of pipes and transportation pipes. And this is always our backbone and where we observe the changes in Vienna. And this is the population growth. The rapid population growth, you see, we are faster than the prognosis of 2030 to pass over the 2 million inhabitants. This is the one aspect. And the other aspect is I have marked it, is the air temperature. The increasing air temperature in summer times, so extremely weather situations in the city. We have a lot of heat days over 30 degrees, and this is very important because for a lot of vulnerable people, the city has to maintain the possibility, or give the possibility to cool down, where we are responsible also for the cooling system. You have probably seen somewhere some kind of airflow devices or some drinking fountains. We have 1,600 drinking fountains that we have also in maintenance for Vienna. This is more than whole Germany has when you compare this. So in Germany, it's ongoing, the project, and they ask a lot, and they make a lot of decisions based on the Vienna way we have for cooling situations. So cooling measures are very important and well accepted. Of course, it's a short-term cooling with aerosols and so on, but I think so mainly these are the aerosols on the upper side, so not from the ground coming up, so directly combined with drinking fountains. So I think this is also a lot of work to maintain the quality and everything through the city of Vienna. So you see the population growth. I'm very too fast. So the population growth going also with the climate change. We see it in our forecast is about 400 cubic meters per day. And in the forecast in 2050, I presume we will be earlier there, is 450,000 cubic meters per day. And if you need a publication which is quite useful for the water demand in Austria, not only Vienna needs water, of course, a lot of other cities and regions in Austria need it, then I recommend the Wasserschatz Österreich, which explains in different scenarios where the water demand in which areas and regions will increase. And the main interest groups, of course, are the water utilities, so the water supply, where the demand will be increased by 15%. This is in very pessimist scenarios already pronounced. Agriculture, of course, there is a conflict of interest with agricultural activities. So groundwater is abstracted for agricultural purposes, for irrigation. And of course, this is sometimes very tricky to manage this with utilities, water utilities. And industry is quite constant, and in total the demand will increase in bad scenarios, as I said, in pessimistic scenarios by 15 up to 15%. Where we see changes is that in the eastern part of Austria, so next to Vienna, close to Vienna, there will be a higher water demand as the groundwater status is lowering down through lower rainfall events and not continuous rainfalls. So it's very important to recharge and to fill up, of course, the groundwater sources. And the need is high, especially in Burgenland, in northern Burgenland, where the demand is great. And we hope that there will not be a kind of Notfall situation where the regulation is already ongoing, how to manage and the priorities for the water usage. I think this is very important to know, that there should be also finally the water demand and the demand for the population should always be on the first side, on the first row, and then the second demand. So the interests are overall very extrapolated. So you see there are different scenarios. This is published already. You can reach out to me if you need some details. But in general, I think this Wasserschatz is a good information and a benchmark to other countries. So the climate change, directly going back to Vienna water. You see, we always balance water. We always check the water quality and how to manage such kind of protection area, which is such as larger than Vienna, how to know or expect what is the upcoming water quality of 70 springs coming from Hochschwab or coming from Ragsgebiet as a large area. What we do, we have a continuous, harmonized quality monitoring systems where we work with different data loggers and where we transfer in real time the data to Vienna and all the central station that we need. So we make a water abstraction in situ. This means that each spring is managed in situ in case of events, rainfalls, problems. We can discharge especially the problematic springs and use to the way to Vienna the special springs that have the best quality at this moment in this minute. But if you listened to my first slide, you know the travel time to Vienna is 36 hours. This means you have to plan already in a few days in advance how the weather will be. So we need a meteorological monitoring, a very important aspect. We know we have a risk-based approach where we check the resource environment and the surroundings. So we have a lot of scenarios that we manage in these regions, and the water pathways to understand the amount, which is a kind of black box. So this is a very important aspect. And we felt it in last year, 24. We had, as you remember, the floods, and also we were partly affected with heavy rainfalls in Vienna and parallel outside. And this parallel situation was very problematic, as some sources, of course, also were vulnerable to heavy rainfalls, and so we couldn't use. So we had a lot of discharge, a lot of water, but we couldn't use all the water. So how to explain someone, we have enough water because it's raining, but on the other hand, you have to use it. So this balance is a very important aspect for the water quality monitoring. And so we observe the rainfalls and the precipitations on a long-term basis in the history. So in general, so these are just some kind of baselines where we see that the rainfalls are locally distributed, sometimes very heavy, but in general, from a statistical aspect, still constant. And the prognosis of this precipitation event is very difficult. Of course, when you look on the precipitation of snow events, that the snow is that has a downward trend, this is very clear to us because this is a very important quality aspect with the snow, the melting time and the distribution on the infiltration to the mountain is very important to us. The slow infiltration melting, which is upcoming about May, where the water quality is then sent out after the snow events. And if these snow events are missing, then we need rainfalls. And these rainfalls should be of a constant precipitation. And this is, as you see already everywhere, it is not the case because we have a lot of short-term heavy events. This was 2024, where we had really an extreme year. And after this heavy rainfall, 4 months were now without any precipitation, any rainfall afterwards. So that was a drought time. So from the statistical aspect over the year, it was constant. But finally, when you look into the specific events, then you have a high-end event and then you have also a very drought event. So managing karst springs is, of course, particularly in the climate change aspect, very, very challenging. So we had the severe floodings. We managed this. We were happy to manage this in time, but we observed this, and these typical climate situations, we see there is a kind of trend all the years, but specific events are falling out. So this is how it looks like. We have different types of springs. So I talked about the vulnerability aspects of karstic springs. They have their own character. This is always what I am talking about when I'm talking about our Dolomit spring types, our limestone karst springs, so as the Kleffer, for instance, is, or our Pfambauernquelle or Kaiserquelle, one of the first abstracted springs in history in 1873. And you see the dynamics, so the discharge levels may change during specific seasons, and the seasonal variation is clear to us, and we can expect this. On some springs are constantly, they are not impressed by weathers and everything. Why that? Because the storage of the water, the fine-tuning of the water and the pathways of the water, in the matrix, in the rock, in the bedrock, is a process of which can last for 20 to 25 years. So we have karst spring waters that are already 20 years old that are now abstracted 20 years ago. The last raindrop fall there. And on the other hand, we have a few hours of difference after rainfall where the discharge increases immediately after a rainfall event because the water paths may be very fast through caves. These are the systems I can show you where we look in the aquifer, where we try to understand the karst system, how the matrix is fractured. And we have also a good collaboration with the Naturhistorische Museum in the Höhlenforschung, where they already have a good look into the caves of, for instance, Hochschwab. We are talking about large cave hole forms, and they are filled up, of course, in rainfall events. And so the water is flushed through the mountain. And this is the heavy event, and the quality of the water must be, of course, here managed. And you see it quite easily here in the curves, measuring turbidity, measuring spectral absorption coefficients. These are the typical management parameters we have. Spectral absorption coefficient is explaining or represents as a proxy parameter the let's say the organic dissolved matter in the water. So it's an indicator that on surface area water was infiltrated, ingressing into the mountain, and so we can decide on these 2-minute distributed values that are logged in time for each spring. We can change to other springs and exit these out. So I think this is very, very important. These highly dynamic parameters are used. They are also proxy parameter for microbiological aspects. So if you follow up hygiene criteria, everybody who is probably has visited a microbiological course knows that typical measurements are lasting for days. This is not the time we have to wait for hygienic decisions. So therefore you need this proxy parameter, and these variables are very important to us, and this is an example how we evaluate our data and have a look at them in typical rain events. So discharge increase after a certain time, increase of SAK, increase of turbidity, and also how fast these are going down, dropping down. And this is the management decision we have. And we know in 2 hours, approximately, we await that we can use the water again and inlet it into the spring main. This is a very important aspect which has a very long research history and collaboration with Medical University of Vienna, Technical University of Vienna, and Karl-Landsteiner University of Vienna. So we have in the course of ICC Water and Health, this is a center research cooperation we have for a few years in the way to understand this karstic microbiological aspect, hygienic aspect on a risk-based approach. So you see the black box mountain here in the backwards. So the details is a geological aspect, but in my division, by the way, I have a hydrogeologist, because this is very important. Geology is the left-hand side for the water quality in mains of karst spring waters. And the ingress of water has different characters, different pore sizes and storage capacity, and we observe these aspects in modeling situations, and we have also karst model, also in collaboration with JRC Aquaconsol. So you see, we are not so far away from the university, and a lot of decisions we make currently are based on a very long-term collaboration with us. So to manage these strategies, we use a lot of types of data. We have the geological information, very important, the meteorological information, where we have the collaboration with Geosphere Austria, where we have here evaluation of data, satellite data, where we look at temporal spatial distribution of rainfalls. We manage these meteorological status, so there are different aids of meteorological stations, so in 1,000 meters, 1,500, 2,000, and so on. This is important because our spring abstraction is in different levels of the mountains, and therefore we have to follow. And so we record every kind of events, and this is important to us. And on the other side, we have the hydrological aspect, where we do dynamics measurements, quality measurements, microbiological measurements, also water isotopes measurements, where the water comes from, for source tracking, tracing tests. This is a lot of historical work where we still use the knowledge until now, finally, to manage water quality aspects. Yes, the time is very short, but yes, this is just an impression of our online near real-time SAK measurements. So these are data loggers that are poured into the water. So you put them into the running water system. So this is working by itself. So measurement, so it can be measured in bypass, but directly in the spring or in the pipe, in the spring main. And in comparison to the historical measurement, you see this glass. And in historical times, what is done, you measured the turbidity of water when you've poured it into this glass tube, and below you could read the newspapers, then the water was not turbid. So, and here we talk about pharmacine units about from 0.1 in the precision of the measurement. I think this is very good, and therefore I think very good future aspect also for the management here, what you see. Yeah. Currently, regarding the climate change aspects, we are learning from the past. We did a lot of trend analysis on a statistical basis, but we're also looking to the future, where we await the future scenarios, the climate scenarios for Austria, where we fill up our karst models with this, or combine the karst model system with the future data climate scenarios, and you see the distribution of the precipitation in winter times, about 1,500 to 2,000 meters. You see it's a very difficult prognosis because in general a constant or an increase of precipitation, not solid precipitation, it is a rainfall precipitation which is here in this field represented. Yeah, what we see here is that the trends are significantly increasing on an annual basis, especially in summertime. from the long-term observations. So we have here the behavior that the quantities are not in total reduced, but we have specific parts where we have drought and the discharge is reduced on a trend, on a long-term trend. This is possible, and also from the snowfall. And you see here for first and second spring water main, just that you have an impression for long-term trends where we have digitalized data, where we have the maximum snow aid, which is reduced for specific parts in regions where we have the spring abstraction. And also the permanent snow field is also on a downwards trend in some regions. The same to the temperature. I don't go into detail, but the patterns of temperature, the increasing temperature, the air temperature is also increasing, and therefore, of course, it has an effect on the snowfalls and on the let's say on the steady state of the snowfall and the snow melt time in a season. So the seasons are changing. We have later on snowfalls. 2 years ago, for instance, the first snowfalls in this region was in February. So the whole winter time before there was no snowfall, and this has and the snow melt is started also earlier than we expect, sometimes in May. And this is very important for the amount of water and the capacity in the mountains. Yeah, to the future, as I said, we await the new climate scenarios. We are collaborating with Geosphere here. And the snow cover, as you hear here, in the bad scenarios, in the very pessimistic, is by -80%. And this is, of course, for the Alps, very drastic. Natural hazards, I mentioned it already last year, but we have different types of hazards in the area where we work. The flooding, the increased evaporation, of course, due to a temperature increase. Also the forest drought, as the forestry department is a very important partner for the protection of water. So we have the so-called Quellschutzwald, and the only work for the forestry department is to ensure that this wood management and everything, forestry management, is for the protection of the groundwater. So we have to store the water with a good soil cover, and this should not be destroyed. And therefore also the strategy of dead wood management. So let the dead trees fall down and let them on the ground to be like a kind of sponge, to ensure humidity in this field and to protect and make a new humus situation. This is a new strategy, also new old strategy, but it's coming up. It gets very important. On the other hand, we have the forest fires. I probably switch down to the next slide. 2021, there was a very prominent forest fire in Mittagstein, which is close to Jahren, close to the Kaiserbrunn-Quelle. This is the main first spring from 1873. And this fire was an increased fire, and it lasted at least 14 days, with a lot of manpower capacity. And then we realized that the fires, of course, according to the fire data structure, this is by BOKU managed, so you can always have a look how many fires we had per year in Austria. So there is a database in the background, Feuerdatenbank or Waldbranddatenbank it's called. And this forest fire was very challenging on the hand to manage, and there was a wind. And on the other hand, how fast will the wood again regenerate and build up? So if you destroy the ground, the soil, and the special trees that are in the protection area, it lasts about 50 years to 100 years that you have a kind of mesh system again, a grow-up system. And a new question arose. This was the water quality, the influence or the impact on the water quality in the groundwater in the spring. So if you have a flow and the fires are burning out the first source part of the soil, the water can ingress also the ash and the turbidity into the groundwater. And so the chemical aspects behind that are really, really challenging. And Canada has these problems. They use the water mostly from surface water. We have the groundwater. And already in the publications in Canada, you see that the surface water quality may has problem in the future has long-term problems in water quality. So here we had a lot of activities and checked out how to collaborate with fireworks and with kind of let's say types of treatments we can use to reduce the forestry, to shorten the time of fires with the so-called tensids. So we are against that. In all the protective areas, these additives are not allowed. And there are specific expert papers that is already today online presented by workers, where we had also a lot of collaborations. I think the new challenges for these aspects are now, let's say, on a next level. Thanks, unfortunately, to a first fire. This was in Mittagstein. And just to that, for your information, the water was not some kind of impacted with problems after the forest fire, because we had a karst part, which was the so-called Störung, and the Störung was too far away that the water can ingress into the groundwater. That's why it's important to understand the mountain inside and to make such models to understand the pathways on a probabilistic aspect, of course. Yeah, and the strategy, one of the most important papers what we use in Vienna. Why we need that? I told you all the reasons before why we have the importance for Vienna Water 2050. Of course, this is a multi-year program. We have a lot of investment requirements afterward, and you already saw in the media that we are already planning and next year starting a new water utility at the Danube Island with 1,000 liters per second to have a power or a backbone also for the first and second spring main in case of maintenance or longer maintenance or breakdown and everything which is necessary. So this is important, and the city is increasing in diameter, so you need to transport more water outside, and therefore the travel time and everything which is necessary should be fulfilled here. We work on a risk-based approach, of course. We have this increasing, so this is one of the most important strategies, increase the water volume produced. So we have sufficient water so far, but we have to manage it also for 2050. So the moment is not problematic, but the future may be problematic due to different causes, of course. And therefore, we build up this new water utility. What we do is in advance, of course, the research, where we do a pilot plant testing in collaboration with technical university, where we do the water treatment aspect. So a very good project, I think, with new data that we achieve on water treatment aspects and quality of water. And the second is to enlarge the reservoirs, also probably realized in the media. In Neusiedl am Steinfeld in Lower Austria, this is the way that the first spring main comes from Rax-Schneeberg direction to Vienna through Baden, and then Gumpoldskirchen and the Weinwanderweg, everything. So our spring main is going there through the vineyards, and before that, the largest reservoirs we have, of course, in Austria. With 600,000 cubic meter with 4 chambers that are currently already since a lot of years working out. And finally, we enlarged the system by 210,000, which is currently ongoing. This is the EF construction stage. Finish this by end of 2030 and continue then with enlargement of GH to 1 million cubic meter storage capacity. At the moment, we can store in this reservoir up to 1.5 days for the whole of city of Vienna in water capacity. So when you calculate the demand, water demand up to 400,000, and you see then the enlargement, of course, that's without the other, of course, reservoirs, but up to 1 million guarantees 3 days at least a storage capacity in case of every kind of fallouts. So it's a lighthouse project, and this is the current construction work ongoing. You see here in a three-dimensional plan, which is a projection in three-dimensional structures with a lot of chambers here, or substructures. So the completion is 2028. It's a very important part. Yes, so these are the, especially the three backbones, and the third one is rehabilitating and extending the pipe network. This is also an important backbone. We say in Vienna, it's the Hauptschlagader of Vienna, are the transportation mains. So when you are staying in a traffic jam or you come up forward, then you know it's mainly a Vienna construction work, where we build up in the second city water main, the third, the fourth, and the fifth. So we connect Vienna with transportation pipes that are in dimension of 1,000 millimeter, DN 1000. So you can imagine that this size with the amount of water without gravity, with gravity transferred from east to the north of Vienna, and they are finally then, the aim is also to be redundant in case of reconstruction or maintenance and also fallouts, that we have always the way from directly end of pipe from second spring water main to the north of Vienna to Behälter Biesenberg. You see the end at the north of Vienna, so the water should be transferred in a very, very short time. So you don't see us, you probably feel us when you open the pipe at home, but all the pipes are, of course, below ground, and you see us just in the construction time. But afterwards, if this is closed, then up to 100 years, there should be a kind of stop. So everybody who does projects will never see, hopefully, again and open this pipe again in his lifetime. This is always our intention. So the work of us is mainly focused on the future. So we do not see the results finally of our work today. So we're working for the next 2 to 3 generations, and also for my children, of course, that they have always appropriate water supplied. Yeah, the sectors I mentioned, it's an overview. The quantity, the seasonal changes, the legal framework is changing a lot in the last time. The water framework program, the regulation, the new drinking water directive, the groundwater directive, everything is now like ongoing, and we try to adapt and implement it on a national level. This is also a lot of collaboration with interest groups and stakeholders to manage this legal requirement and to protect the water from private aspects, from privatization and so on. And this is not possible for Austria. In different other countries, it is the case. The quality aspect, we have to manage in future the fast events. We have to be crisis prepared. We have to be prepared for natural hazards, and also implement treatment strategies for these heavy events. This means disinfection strategies, treatment strategies for turbidity, to manage all kinds of types of water, raw waters that we have to produce into drinking water. And the operational control, this is the follow-up. This is very important. We check up about our data, the storage of data, the safety of data, because as we are a critical infrastructure, we have to manage our data very carefully and save our data, that we have no kind of problematic situations. So do not fall in this situation at all. So I don't have the feeling for the time at the moment, but you didn't raise your hand, so I expected I was appropriately in time. Thank you for your attention, and I hope I could give you a kind of impression of our work and strategies. Thank you.
Thank you very much for the talk, and we'll come back with questions later. But I want to right away introduce our next speaker, Atakan Aral. He is currently an assistant professor of information systems engineering at the Faculty of Computer Science here at the University of Vienna. He originally conducted his doctoral studies in computer engineering at the Technical University in Istanbul. Since then, he had stations at the Technical University here in Vienna, Umeå University in Sweden. And as I've said, since last year, he is assistant professor here at the university. And very important, he's also a member of the ECH that we're talking about a lot, which I'm quite happy about. He's working on this intersection of computer science and environment, which is actually also where I'm coming from. So I'm very much looking forward to your talk. And it's great that you're here. And welcome to the stage. And let's start the presentation.
Thank you. Great. Thank you very much for the introduction. So as Timo said, I'm a computer scientist, so I will mainly talk about not the water quality itself, but technologies from sensors to networks to algorithms that we use to monitor water quality. So my research area is distributed computing systems, but I apply this to sensor systems, which include, among other things, sensors for water quality. So the work described here was also done in my previous institutions. I will not repeat. Timo already mentioned that, thanks to our generous funders. I would like to directly start with a use case or a problem that I find very interesting and motivated me to work on this area. And it is about water treatment plants. So industrial facilities in watersheds use river water for their process, like diluting, cleaning, whatever process they have, and then they release it back to the river. Of course, they have water treatment facilities which clean the water from any pollutants when released back to the river. But unfortunately, these water treatment plants or water treatment facilities are not always reliable. And there have been several accidents. I only have the ones in Europe here, but worldwide this is a big issue. For example, in Kokemäki River in Finland, in 2014, a nickel processing facility released tons of nickel to the river, and it was detected 30 hours after the incident. Similarly, in Poland, in 2019, in Vistula River, a water treatment plant failed, and hundreds of tons of nitrogen and phosphorus was released, and it was detected, first noticed 5 days after the incident. And yeah, similarly, in 2022, in Oder River, there was so-called mysterious massive fish deaths. Again, the disaster was detected only after environmental impact already happened. So we detected those, for example, the one in Finland, after mussels died, and here after fish has died. So our idea was, can we speed up this detection process so that we can reduce it to minutes or at least hours rather than days. And we formed a European-wide consortium in 2021 where we deployed an early warning system for European rivers. For now, you can ignore this server part, edge and cloud servers. I will come back to that very soon. But the main idea is we deployed measurement stations, many measurement stations along the river, and collect real-time data. So using very similar sensors my co-lecturer has mentioned, like turbidity sensors or organic matter sensors in real time. We collect this and monitor water quality. This is the easier part, but there are challenges still. I will also come to that. But the more difficult problem is that is to model, create a model of the water flow in this river network to predict the source of the pollution. So we detect the pollution, but in addition, we use advanced machine learning algorithms to estimate where this pollution is coming from so that the authorities can take measures. So I will come back to this project soon. I actually continue with that project, but I will come to that picture soon. These were our use cases. So we had partners from Finland and Turkey. In the case of Finland, the same river that I mentioned that the nickel disaster happened, Kokemäki River. And the importance of this river is that the water is used as artificial groundwater and used as the utility water of the city of Turku, which is one of the biggest cities in Finland. And any pollution on this will reach the utility water after several days, of course. After several hours. The second use case was the Ergene River in European part of Turkey, which is shown in this map. I don't know if it is clear enough, but there are tens of industrial zones in this area. Especially textile industry is very widespread there. Use river water as well. And then in the downstream rivers, shown with orange color, there are agricultural areas which use the river water for irrigation. Again, this is a time-sensitive situation where any pollutants could reach the crops and eventually reach humans. So we worked on these use cases, these two case studies, and deployed prototypes of our approach. And as I said, the main challenge was the predicting the source of the pollution, but also monitoring was kind of challenging because we are not in a city setting or an urban setting here. These rivers pass through forests, mountains, in very remote areas. So we are off-grid. We don't have access to electricity easily. We don't have access to high bandwidth networks. So the two projects, so the first project I mentioned is the SWAIN project, Sustainable Watershed Management through AI Technologies. We monitored water pollution in this use case as a case study of environmental monitoring, but there are also possible applications to forest fires, avalanches, landslides, everything that requires real-time monitoring. Another type of off-grid sensing is man-made infrastructures, like critical infrastructures, like water distribution networks, agricultural areas, and oil and gas wells, which are all usually in remote areas and outside the borders of cities where we have developments. So we made a systematic study of this kind of rural or remote environmental monitoring or sensor systems. And we analyzed the common aspects that are common challenges found in this off-grid setting. The first challenge was, as I said before, electricity access. There was also a problem with internet access, or connectivity. Failure risk was usually high. And we also considered impact on the natural environment we are monitoring. We cannot blindly deploy sensors, bring electricity through new power lines, and build network stations in the middle of a natural environment. So we also wanted to reduce the number of the amount of deployment in these natural areas. So now I come back to this edge cloud server picture. We use the technology called edge intelligence or edge AI. In computer science, edge means edge of the network. So in network science, let's say, edge of the networks, which means not a computer facility in a remote, in a long distance area like a cloud data center, but something close to the users, a computer in our house that collects data from our house and does the local processing. So this is edge computing. So the definition is, instead of entirely relying on the cloud, edge AI must make most of the widespread edge resources to gain AI insights. And in an urban settings, as you see in the image here, we have many mobile devices generating huge amounts of data. The purpose of edge is to play a middle role between these data generators and this data consumer, which is the cloud, as a middle layer that can process the data locally. For example, the purpose could be have more privacy rather than sending everything to the cloud, or reduce latency because sending data to cloud takes time. So this is how it works in an urban setting. As I said, edge servers are located closer to the data sources compared to the cloud data center. This brings a higher data transmission rate at the cost of lower computational power. So they are not as powerful as cloud, but closer to the data. So how this connects to our environmental monitoring use case? As I said, these measurement stations are in very remote areas, so we cannot live transfer all the raw data from these stations to the cloud data center. So the solution we had was to deploy very low cost, very low energy consuming devices near the sensors that process the data. So these are so-called edge servers here. Multiple measurement stations connect to an edge server, and some kind of local modeling of the river goes on in this edge server. Only periodically, say every 1 hour or every few hours, these local models are communicated with the remote cloud data center to have a like a better bird's eye view of the whole river model. So by doing this, we switch from continuous data transmission from measurement station to cloud to something we can do every once a while from an edge server to the cloud server. And also we don't send raw data, low sensor measurements, only insights we learn from this data. So as I said, we focused on the sustainability of these measurement systems or sensor networks. And when people mention sustainability in computer science, the first thing comes into the mind is the energy efficiency, because computers consume a lot of energy. But beyond that, there are challenges like battery life of devices, because you leave them in the environment and you have to dispose them, you have to maintain them. Hardware can become obsolete over time and generate e-waste. Again, deploying those in the natural environment have physical disruption, have a carbon footprint of manufacturing and installation of these devices. So I collaborate with these sustainability aspects with partners from the ECH continuously, and within the some of the solutions we have came up with was energy harvesting systems, which are, as I said, these edge servers are low energy consuming, so they can generate their own energy. They can have solar panels attached to them, or in case of river monitoring, they can have turbines that generate energy, and we don't then need to bring electricity to these locations. These devices can turn themselves on when there is no interesting data and wake up when the data is more relevant. This is called duty cycling. We also strive for deploying fewer sensors and fewer sites. And we also try to reduce the amount of communication, usage of network between the devices, between the sensors and the edge servers and to the cloud. And of course, we also make the processing more efficient to consume less energy, because we are limited with energy. If it is solar at night, we don't have, so we have to use a battery that's, and not to deplete it, we have to be very efficient. So in these two case studies, we focused on so-called spatial planning of sustainable IoT deployment. By the way, if you don't know what IoT means, it is for the scope of this talk, it is just a sensor. So deploying sensors in a very large scale area to preserve data quality, reliability, maintainability, accessibility to electricity and network, the cost of deployment, and effect or footprint on ecological environment. And some of these are contradictory goals, because to have better data quality, you need more sensors, but this is more costly and this is less sustainable, for example. So in one of our works, which was the main final publication of this project, which has recently ended, by the way, was a framework called GANS. The name comes from the names of the first letters of the names of the 4 modules: gateway placement, energy modeling, sensor network modeling, and sensor placement. The idea was to start from an initial placement of sensors, because in many areas we already have station, we already collect data. So we start from an initial placement. We deploy not only sensors, but also network gateways that connect these sensors to the global network. And our solution also generates not a single solution, but trade-off solutions, or a Pareto solutions, that can optimize number of sites, network accessibility, data quality, or energy. And if you are interested in machine learning, you can of course check the paper, and the method we used in this work was column pivoted QR decomposition. And this is one of our results. Here you see the original deployment on the left side. For you, it's on the right side, no, left side. On the left side, you see the original monitoring stations. This is the river Ergene in Turkey. And then our algorithm deploys gateways that can cover most of these sensors based on how much informative data they are producing at each sensor. We reduce the number of gateways and select the most important sensors. And then on the third step, we remove some of the sensors and keep the most relevant ones. And by this way, we can reduce the number of sensors deployed by up to 73%. So in our original, in the previous deployment, before we applied the algorithm, there was 75 measurement stations. We reduced this to 30 stations, and we still were able to detect the same number of pollutants. So the data quality didn't drop, but we had huge energy savings and less impact on the environment. So maybe it's a good point now to connect to the question and answering phase. I want to talk about what can be done and why we have to act now, because as the previous talk very nicely introduced, problems and risks, climate-induced risks in Europe are rising. There are more droughts, floods, and pollution risks. We need, for resilience, we need timely data and rapid response. And in our group, we can deploy low-power sensors and edge AI to reduce energy bandwidth and latency while enabling local decisions in remote off-grid spots. We would like to align with policy. We would like to design pilots that directly support Water Framework Directive. And so far, the project that I mentioned was, this was for river water quality, but we also started another project very recently focusing on water distribution systems, so collecting samples from water distribution networks, but I didn't include that in my presentation because it's a new project. We don't have interesting results yet. So in both cases, in both projects, we focused on mostly basic research. So developing the technologies, but not applied or widespread deployment of these technologies. So our idea is to also start local, collaborate with the city of Vienna, hopefully, plug our solutions into existing digital water infrastructure for early warning pilots. And you as a participant of this lecture, if you are a researcher, please feel free to connect with us if you would like to contribute to the model, algorithms, or data sets. If you're a student, you can join a research project with us. If you are with the city, utility, or NGOs, we would be happy to work with you on having pilot sites and etc. Or if you are with industry, we are interested in hardware and connectivity solutions for the use cases that I mentioned. That is the end of my talk. Thank you very much. And I think Timo will take over. Thank you.
Thank you very much, Atakan, for this talk. And I'm just welcoming both of you back, or you're already on the stage. So before I'm giving the floor to your questions or the questions that might be online, I think why the topic of water was very interesting for me also in the planning is because it is one of these things that Ulrike Feld would probably consider as an invisible infrastructure, or the invisible infrastructure around the water, because I think we have seen very nicely that in order that we all here have our water and we just open up the tap, it needs so many things. So thanks again for showing this complexity. And I was just wondering, needing engineers, microbiologists, hydrologists, maybe also like legal scholars, because there are obviously probably also regulations you have to obey, computer science and so on. So what are your both experiences with bringing these very different people together with their backgrounds and the challenges and how you deal with that? So maybe let's start with Atakan.
Sure. I think finding a common dictionary was a challenge in the beginning for us, because, for example, when we worked with environmental scientists, and they said that we need real-time systems. If there are any computer scientists in this room, real-time system means nanoseconds for computers. If something is real-time, it happens in nanoseconds. But in environmental science, of course, even something that works in a couple of minutes is real-time enough. So this was one interesting aspect. So as I said, finding common language, common dictionaries is very important.
We have our demands, as you saw already in our presentation. So the demands are already historical. So 30 years ago, we have initiated the collaboration with researchers, hydrogeologists, geologists. So this is a long-term project, as of course nature and environment is a kind of a large structure which is already unknown, and there was a vision of technicians 150 years ago to produce or build up a pipe, which was a very innovative aspect, and thanks to Eduard Süß and co, who was, by the way, a geologist, so a very important man to us. And I think this long-term strategy, research, investment in research, is still the way we are going on to gain new knowledge and new insights also in these technologies. So we are highly interested in new technologies regarding the data build up and the structure of data and the transfer of data to for decision-making processes. And from the regulatory aspect, of course, we are a city of Vienna, so a lot of lawyer specialists are working in different types of divisions of Vienna, so the collaboration is very strong with water departments. And hydrogeologists, of course, in my quality departments, for instance, there are geologists, microbiologists, laboratory collaborators, and also external labs. So we have a high communication with different disciplines, and this is, of course, very important. So just to maintain these connections.
Thank you very much. And with that, I'd like to open the floor for your questions. It seems to be that the talks were very clear, which is good. So I just repeated for the live stream. So the question was about there are some areas where groundwater is taken, right? And the question was if now the population grows, which we can suspect, what might be the impact and how do you deal with that on the groundwater if you would need to take more of the groundwater?
Regarding our groundwater works surrounding Vienna, we are not confronted with lowering groundwater levels, as these types of aquifers have a very high storage capacity and are very protected, especially also the Lobau region or from the island. We have the riverbank filtrates, so there is water quality of waters like the Danube very important. So and also in the southern part of Vienna, in the Wiener Becken, it's one of the largest aquifers in Europe with a high storage capacity. So there, in certain points, yes, but especially for the waterworks surrounding Vienna, it's not the aspect. But in Burgenland, as I already mentioned, they are faced with lower groundwater levels in the near future, and also this summer and last summer. So there was really a precarious situation at this time. But the need will increase for groundwaters. So it's also for Vienna. We have at least 10% amount to the karstic spring waters. I think this is something special. In Vienna, we are really in a special situation. I think when you look into other cities in Austria, you will realize that a lot of cities are not supplied by karst spring waters. Salzburg, Tirol, partly, Kärnten, surrounding of Klagenfurt, mainly, and the rest is groundwater. And for Vienna, the understanding on groundwater is probably not well understood, as karst spring waters and groundwaters are the same. They are also groundwaters, and 98% of Austria is supplied with groundwater, and the quality and the protection of the groundwater is on a very, very high level. I recommend you also the Trinkwasserbericht, the current one, 2025, which published all the data from water utilities in whole over Austria, and the quality of or let's say the deviations on quality published in this report are by below of 1% in quality parameters. So the groundwater is really protected and on a very high level, but this is a big challenge for all water utilities to go with this aspect because, as I said, irrigation, agricultural activities, nitrate, and the persistent pollutants, the mobile pollutants, as you heard already, coming from the atmosphere partly, are a very relevant micropollutant aspect when you look into rainfalls and so on. This is the challenge that we have, but from the amount of water in Austria, it's just a problem in certain regions, but the quality in general, I must admit that we are really in a very privileged situation in Austria.
Thank you very much. Are there any further questions from your side? Yes, please. Yeah. So the question was about if it's possible for the Viennese system, I think specifically, to split kind of different qualities of water, saying that, you know, there's the drinking water that has to be a very high quality, but then, for example, to flush the toilet, there could be, you know, a lower quality of water. Are there possibilities to do that, to kind of split that up?
I can give you a first answer is, as we are drinking water utility, responsible only for the drinking water aspects. The wastewater treatment is second step, which is from the EBS Vienna, for instance. And you mean the intermediate quality, like the gray water or polluted water, semi-polluted water. You have to imagine how to abstract this water and how to transport this water into the main regions, or for instance in flats for the toilet flush. You need to maintain two types of pipe systems next to the heating pipe system, and the responsibility for water is not in the responsibility of the drinking water utility. Of course, it has an it has a good aspect, but this means an investment for Vienna would be at least 3,000 kilometers of pipes for grey water to use it for different types of flushing or, I don't know, irrigation purposes, whatever. So I think this is a technical challenge. The idea is fine for some local areas, or if you have a groundwater in a region in Vienna that you can abstract and use it for irrigation. This is clear, and I know a lot of buildings in Vienna, they use this groundwater also for toilet flushes, but the experience shows that sometimes the maintenance of these groundwater boreholes is not ongoing well, so they get problems with corrosion, so the particles are coming into the pipes, so they have a lot of problems in the maintenance for the pipes, and you have to invest a lot of money for the maintenance of these groundwater abstraction zones. And I think people are not aware for the investments costs of these types of water. So you have to maintain the let's say the brunnen in the area for this irrigation, and if you do not maintain it, and we have to regenerate such types, then it can be an amount of money of up to 100,000 euro, and for a house building group could be a big investment and a big financial problem. So I can imagine in the future for local, but for the whole city, it's very challenging from the responsibilities and from the construction.
So I've seen there was another question, but just to stick for a moment with this quality question, because for you, Atakan, I was wondering, when we're talking about pollution, there are some pollutants we know very well today, and we have a lot of people in the ECH working on pollutants, so that's why I think it's a big topic for us. But then obviously there are also always new pollutants coming up, new forms. How could we use the technologies you were presenting also to maybe deal with that? Would it be possible to use these machine learning systems to also look at things that we might not even know yet? How have you engaged with this question maybe?
So not directly with unknown pollutants, but we had the challenge of not all pollutants can be measured in real time. You have to take sample, and the analysis take hours in a lab. You cannot do it in situ and in real time. So for these, we actually had the that you mentioned. We used machine learning, analyze historical data, and try to find connection between parameters that we cannot measure and parameters we can measure. So this works mainly.
Thank you very much. And I think, yeah, Jutta. So the two questions were the first one about is there any data already showing that groundwater that is used for Vienna, for example, is heating up, or is temperature changing in general? And the second one is about the geothermal use of groundwater and what the effects on the groundwater are. If you're looking at that, and what you know kind of about possible effects there.
Regarding groundwater temperature in Vienna, exactly. If you mean Vienna, in the city of Vienna, there was a big project, heat below the city. Probably you already were visiting the presentation of Professor Griebler et al. And obviously there is an increase in temperature in certain areas of the city, of course, as expected in the center city, and also in parallel they managed to observe the microbiome change and the change of the ecological aspects in these groundwaters. So in our waterworks, we do not observe these temperature changes, as the water is stored very long time stored in this capillary water aquifer. So therefore we are not confronted with these temperature increases. Also not in the spring area, in the mountain area. Probably from the prognosis in the future, yes. But at the moment we are, let's say, we are supplying about between 6 and 8 degree of temperature during all the year. And this is what the start temperature coming to Vienna is finally. This is also, let's say, a good privilege. I must admit, in the groundwaters, there are higher temperatures than in the spring waters, so they may be up to 10 to 15 degrees. This is an experience. This is also a seasonal variation we observe, and I think this is in Austria also the case in some parts, also again in regions where different types of extractions are performed. To your second question, we are in the city of Vienna. There are strategies, as you already said, in specific. Seestadt is one of the. For Vienna water, it has currently no impact, but the challenge is in the surrounding, like in Lower Austria or everywhere where these boreholes are performing. I think the challenge for the groundwater temperature increase are there. This is also scientifically discussed and partly proved, and also the cooling systems, these Kühlmittel system, that they may support the organic dissolved matter in the groundwater and change the microbiome in the groundwater, which should be very stable. And I think within the water resilience strategy, the microbiome and the ecological aspect and characterization of groundwater is one of the strategies, and these things might change the system. From a utility aspect, it is interesting because it's a kind of conflict of interest. The water demand for these types of water, they're probably in different depths of water abstraction than in the drinking water aquifer. But nevertheless, it's important, I think, to maintain a kind of registration of these geothermal utilities. And I think this is important that we are, as water utility, informed that this is happening in surroundings of, for instance, groundwater works. And I think at the moment it's not directly the case through, I don't know, bureaucracy issues. Yeah, I hope I could somehow understand.
Thank you very much. And by the way, because you mentioned him, Christian Grieber is also a member of the ECH, which is great. So by the diverse expertise there, and actually what you were mentioning, the microbiome is not only it's for the water, it's an important topic. What we noticed that it's in a lot of areas, it becomes more important to look at kind of this aspect in the last years. I think we would have time for one more question. Yes. So the two questions were about, so Atakan, you were talking about that the sensors in the water systems can hibernate so that they are not turned on, let's say, all the time, and how that works now that it understands that it has to power up. And the second one was about the transmission of the data now from the sensors to these edge servers. How does that work? You know, what are the ways of transportation, possibilities or limitations?
So for the first part, I think the misunderstandings, the sensors do not turn off. The computing devices near the sensors turn off. So the sensors continue feeding data, and in the servers, edge servers, we have two different models. One is extremely simple anomaly detection algorithm, which consumes almost no energy, and when it detects nothing, the main algorithm doesn't run. So the device is kind of in idle power. When we detect an anomaly, the full model starts running. This is one way of duty cycling. There's a second version, and this is for solar-powered or energy harvesting devices. These devices work when there is enough energy and save their states. And when the energy is behind the threshold, they turn off. And when new energy, enough energy again accumulates, they turn on again and load their saved state and continue from this point on. So these are the two ways how we do it. The second question, for communication between the sensors and the edge nodes, we used a protocol called LoRaWAN. This is low range, very low power energy communication method. This is mostly designed for smart home appliances like our within our apartment, like smart lights or sensors, they also need to consume very little energy because they are powered. So this technology was designed for that, but in an open field, its range can reach several kilometers. So this is what we use in this case.
So I'm always trying to ask the kind of the last question to all the speakers, always the same question. So it feels like that the water topic is a topic where this combination between knowing and action works quite well from what we've heard. But anyway, there might be still room where you're saying, where there could be improvement. So what would you say, where could we get better in terms of from knowing to action? Where are maybe blind spots that we need to work on from both of your perspectives there? So I'm just starting with you.
Thank you. It's a difficult question to start with. I think basic research is very important. We should have the foundation already developed enough to be able to start working on more applied and more collaborative research ideas. And I believe we are in that point right now, that we have the methodologies, and we just need to listen to stakeholders and see what their requirements are, and come up with solutions and pilot systems for those.
I think there are a lot of future demands we have, but one thing is, we talked about micropollutants, and I think the message sometimes I hear is also from the public and the sectors and the stakeholders is, yeah, there is a water treatment, and finally we get rid of all the micropollutants. We are, as water utility, a kind of end-of-pipe solution, and instead of protecting our groundwaters according to the Verschlechterungsgebot, the problem is that there is no enhanced producer responsibility for of micropollutant substances, and according to the Water Framework Program and different types of EU strategies, this is written on a paper, but in practical aspects broken down to Austrian situations, or pollutants, direct pollutants where you have traces and you know the pathway, you don't have any possibility to reach out to them. You don't have the data, the emission data from riverine regions or close nearby, or from agriculture, what is applied, is there a registered application of pesticide, herbicides, or other pollutants, and we are at the end of the pipe, and if something happens, we are the solution, we have to treat the water. And you know, the consumer response is finally, you have a natural spring water, why do you treat your water finally? So if we do not protect our groundwaters now for the future, then our karst spring waters and everything surrounding Vienna in the future needs to be treated in a 100% way. And now we virtually treat our water because of our actions we do, and really collaborate also with stakeholders, are going to the fronts, let's say it like that, and challenge also with them. But let's say the enhanced producer responsibility is not lived and realized in Austria so far, and this is, I think, very important for our future water demand. Yeah, that's my message. Last message, finally.
Thank you very much. So thank you very much to Atakan Aral and Maria Zunabovic-Pichler for your presentations. I think it was very interesting, very insightful. So thank you very much. So also thank you to you for being here, for your questions. And I just want to highlight again, because we are getting this question quite often now. So the recording will be available around latest 48 hours after the session takes place. Also the presentations will be uploaded, because sometimes people write us half an hour after the session asking where these things are. We will upload them to Moodle when they are there. Please also always take really a look at the materials. They are not only the presentations, but also further materials the speakers provided, and sometimes even additional information that we just added. So next week we will be talking about the mobility of the future. And we will talk about different modes of transportation here in Vienna. I'm very much looking forward to the both talks we will have next week. Thanks. everybody for being here on the live stream, and hopefully see you next week. Thank you very much.